Hello everyone, my name is Chandralil Chakraborty from UC Santa Cruz, advised by Professor Hanelitz. Today I'm going to present my work on reducing write amplification in Flash by dead time prediction of LBAs. In log structured storage systems such as SSDs, data is not updated in place but appended to a log. The log maintains multiple versions of the same data, where the most recent version of the logic element is considered valid, whereas all other versions are considered invalid. To bound the storage capacity of log structured storage systems, garbage collection needs to be performed to remove the overwritten data elements from the log. Garbage collecting a block requires all valid pages to be moved to a new block, and only then the clean block can be erased. Now, this garbage collection process requires over-provisioning in SSDs to copy the valid data to new blocks. This extra writes overhead results in reduced lifetime. During GC, it's typical to see high tail latency. As a result, cloud service providers cannot guarantee an I/O response time. As previously mentioned, GC is the process of recycling invalidated stale pages to free blocks to free up space for new incoming data. The GC overhead can be measured using write amplification. Write amplification is the ratio of the number of pages programmed within the SSD to the number of page updates issued by the host. The magnitude of write amplification depends on factors such as over-provisioning ratio, the mapping mechanism, and the write patterns. For applications that exhibit sequential write patterns with uniform write frequencies, write amplification tends to be low, as there is high probability that LBAs within the same block are overwritten with temporal proximity. However, for most applications, the write frequency tends to follow highly skewed distribution, resulting in increased write amplification. We define dead time of a data element as the number of I/O writes before which the data element is overwritten. The key idea is to group LBAs with similar dead times together within the same block. Assuming there is sufficient number of open blocks, write amplification can be achieved, which is an ideal placement strategy. We introduce the basic operating principle of our dead time aware policy with this example. In this example, we have an SSD has two LBA in their SSD, each block can have two LBAs, and we observe writes to three different LBAs, A, B, and C. Now, in the table, the first row shows the elapsed time, the second row shows the LBA sequence, and the third row shows the corresponding dead time. Rows 4 through 6 shows three different block allocation policies and how they place LBAs into blocks. And the policy strives to achieve as few blocks as possible to store the data. Now, the fourth row shows how a conventional baseline FTL that applies write sequentially to a single open block will observe the write sequence. The first two blocks are written into the orange block. At time 3, the orange block is closed and the blue block is opened. At time 5, the orange and the blue closed blocks still contain valid LBAs that we can see based on the dead time information on the second row. As a result, the green block is opened, absorbing the next writes. At time 7, the blue block can be reused as all the LBAs within it has been overwritten. This policy requires 3 blocks to absorb the write sequence. The fifth row shows the operation of a hot-cold based allocation policy. LBA-C is considered a cold LBA, whereas A and B are considered hot. As a result, at time 1, C is placed into orange block, whereas A and B are placed into the blue block at times 2 and 3 respectively. At time 4, the blue block is closed and a new hot green block is opened. At time 7, both A and B within the blue block has been overwritten, enabling us to reuse the blocks as blue block at time 7. This policy also requires 3 blocks to absorb the write sequence. The sixth row of the table shows how our dead time allocation policy allocates LBAs into blocks. LBA-C written at time 1 and LBA-B written at time 3 have similar dead times of 5 and 4 respectively, and hence they are placed into the orange block. The LBAs written at time 2 and time 4 are placed into the orange block. At time 5, the dead times of all LBAs in the orange block have elapsed and hence it can be reused. Oracle DT minimizes the number of blocks currently in use, requiring only 2 blocks to absorb the write sequence. In this work, we make the following contributions. We present a data placement strategy that can guarantee zero garbage collection overhead, having perfect knowledge of LBA dead times. We also present a practical approach which uses machine learning models to predict dead times of LBAs and present the design of MLDT. Finally, we experimentally show that our approach outperforms the best performing baseline by up to 14%. For this work, we leveraged traces from 10 real-world workloads from 3 different sources for our experiments. All traces were collected at the block I/O level, and we can see the characteristics from the table. All the traces in general were write-heavy with more than 0.5 read-write ratio. Upon analysis of the trace, we make the following observations. Real-world workloads exhibit skewed write patterns that we can see from the figure on the left, where a significant portion of the I/O accesses were covered only by the few LBAs. As a result, the distribution of LBAs has a long tail, as can be seen from the figure. The death times of LBA vary widely from a few IOs to a few thousand IOs. Hence, separating IO streams based on death times enables us the invalidation of plagiaries within the block solely via user writes. We also found that user writes originating from similar location tend to have similar death times, which is in line with prior work. Hence, the LBAs of IO writes can be used to separate streams of data with similar death times together within the same block. We also found that for a given LBA, the death times change over time. Hence, the prior history of assigning LBAs to blocks can be inefficient, resulting in higher write amplification. For our work, we consider two features as input to our models, the LBA and IO size. We separate each LBA into two parts. The upper and lower significant half of the bits are separated and then hashed into range of values 0 to 100. This allows the model to distinguish between the interleaved IO accesses using the higher bits while predicting in a stream using the lower bits. In addition, the full LBA is also normalized to a value between 0 and 1, where 1 is the maximum LBA size. In order to reduce the number of possible IO size values, we round off each observed IO size to the nearest possible value of log of that value and use it as a feature. This reduces the number of possible IO sizes to 16 while still supporting request sizes up to 64 megabytes. The proposed model architecture is shown in this figure. The inputs to the model are categorical one-hot representation of the input features, each being fed to a separate embedding layer for dimensionality reduction. The sparse embedding vectors are concatenated and then fed through dropout layer of 0.2 to prevent the overfitting of the model. The death time prediction is performed by a temporal convolutional net layer, which is a variant of traditional convolutional neural network, CNNs. TCNs employ causal convolutions and dilations to learn from sequential data with temporality. As TCNs implement memory using the causal dilated convolutions, it considers recent data to differentiate between the interleaved IO access. TCN also track the behavior of IO access and how they evolve over time, which enables us to make accurate predictions based on the current state of the system. We empirically observe that having two hidden TCN layers is sufficient, where each layer has 500 neurons. The final output layer is a dense layer consisting of software nodes. The number of neurons in the output layer is set to the number of open blocks available in the SSD. Our training is trace specific. To leverage MMLDT, our model needs to be integrated into an FTL. We assume a flash-based system supporting n+1 open blocks, where n blocks are assigned for servicing user writes and one for servicing GC writes. Although Oracle DT does not need a GC block by eliminating write amplification, MLDT cannot provide such a strict guarantee and hence needs a GC block to absorb the read GC writes. Each one of the user writes is assigned a death time range for user write, and the block with the closest death time range is chosen for placing the write. The death time ranges are set according to the nth percentile of death times and the number of open blocks for user writes. For example, for a system with 11 blocks, we keep 10 for user writes, 1 for GC writes, and block out of the 10 blocks, block 1 will store death time range in between value 0 and 10th percentile, block 2 will store death time values between 11th and 20th percentile, and so on. Each block maintains a death time counter which is initialized at the maximum value and decremented for each IO. If the death time range of a block is chosen optimally, the death time counter reaches 0 only when the block is full. However, as our ML model is imperfect and number of open blocks is limited, if the death counter of a block reaches 0 with the block not being full, it is assigned incoming pages from the adjacent to the nearest death time ranges to close the block as quickly as possible. And the death times are recomputed for all 3 blocks using the formula provided. If after a programmable amount of time, the block still doesn't get closed, all future IOs are referred to as priority writes are redirected to the said block to close it. We keep track of the number of user writes, GC writes, and priority writes used to store the data and compute write amplification as shown. For our work, we utilized 4 baselines to compare our approach: random forest support vector machine LSTMs and random predictor. To evaluate performance of LSTMs, we replaced TCNs in our model with LSTM layers Random forest and SVM models were fed 2D data input. The table shows a comparative performance of our ML approach against 4 chosen baselines when only using 19 dead time classes, and 1 is used for GC writes. The LBAs without data information are excluded from training, and we train our models using the first 50% of the data and evaluate on the remaining 50%. The size of input traces range between 0.47 GB to 43 GB depending on the source. The results from the table show that our TCN-based approach consistently outperforms other baseline techniques, and the random predictor performs the worst, achieving lowest accuracy. The results from LSTM model were comparable with our approach within 5% of accuracy. However, the TCN-based model trains 10 times faster and reduces inference latency by up to 2 times. Random forest and SVM approaches perform significantly worse, achieving highest accuracy of only 61 and 56%. We compare our work with three baseline data placement policies. First is dynamic data clustering, DAC, which maintains multiple open blocks and assigns each one a temperature. Whenever an LBA is overwritten by a user write, it is promoted to a hotter block, and whenever its LBA is moved by GC write, it's demoted to a colder block. Next is AutoStream, which leverages both write frequency and recency to determine the block temperature, and it uses it for writing pages into blocks of different temperature levels. It also demotes aged LBAs into cold blocks. Warship writes pages into blocks based on block update interval, that is the elapsed time since the last write to the same LBA, in order to reduce the variance of update intervals within a block. For all experiments, we used an over-provisioning ratio of 0.2, and 0.1 was the GC threshold, 0.1% of the number of blocks. So our approach reduces the number of GC writes due to effective placement, and priority write overhead is minimal, which causes less than 1% overhead. From the figure, we can see that DAC performs the worst, while Warship and AutoStream performs the best among the baseline, achieving comparable performance on TPCH benchmarks with lower number of blocks. However, they perform much worse on VDI-based workloads, and Oracle DT achieves near optimal write amplification for RocksDB and VDI traces, and as expected, performs best. Our approach, MLDT, works best for VDI and RocksDB traces where I/O patterns are non-uniform and our access are concentrated on a few frequently occurring LBAs. The performance is comparatively worse for traces which have more uniform distribution of LBAs in the trace, for example, TPCH. These slides compare the performance of our approach with the baseline by varying the number of open blocks available. The results shows that our approach is comparable to baselines when using a smaller number of open blocks. However, as the number of open blocks are decreased to between 10 and 30, our approach outperforms the baseline by 19%, demonstrating the generalizability of our approach with varying number of open blocks. In this section, we perform a sensitivity study to evaluate the impact of varying number of open blocks on write amplification. For each trace, we vary the number of open blocks between 5 and 30. We see that increasing number of open blocks increases the write amplification initially due to better organization of data within the SSD. However, as we increase the number of open blocks to over 25, we see a decrease in write amplification due to decreased predictive performance of the ML models and the fragmentation of data within the SSD. This trend can be seen from the figure. Thus, to summarize, in this work, we leverage time series nature of I/O writes to train lightweight TCN-based models to predict death time ranges of LBAs. We presented the design of MLDT and compared our approach with 3 state-of-the-art data placement policies. And we show that our approach results in up to 14% improvement in write amplification compared to baseline technique and generalizes better with increasing number of open blocks. That concludes my talk. Thank you for listening. I will take any questions that you may have. Thank you.